In this video, I'd like to go over these three examples of taking a Laplace transform of a function. And as we progress through these three different examples right here, the complexity of the function is going to increase. So we're going to start with example one, which is probably the easiest type of Laplace transform we can take. And x of t is equal to 10 plus t squared. Now over on this side, I have two tables that I've put on the screen. The first one is properties of the Laplace transform. The second one down here is different Laplace transforms for different functions that I've sort of cherry-picked from Palm System Dynamics book, and that these particular ones will help us with the functions we will be working with. So back to example number one, 10 plus t squared. Now we have two different terms here with a plus sign. So what that means is we're going to have to deal with each of these terms individually. Now if we look at 10, 10 is just a constant. So if we go down to our table right here, we see entry number 3 is dealing with a constant c. If we say that c is equal to 10, then when we look at our Laplace transform over here, we see that it's going to be 10 over s. So that's what we have. So the Laplace transform of our function is going to be equal to 10 over s from entry 3. And now we look at this second term right here. Well, what's going on here? We have a t squared. So let's look at our functions. And it looks like entry number 5 will be useful. And with entry number 5, if we have n is equal to 2, let me pick a color that is black. So n is equal to 2, then 2 factorial is equal to 2, and s to the n plus 1, so it's s to the third. And that's our second transform. So we're going to have, this is going to be 2 over s to the third from entry number 5. So that's pretty much as simple as transform as you will see. Now let's go to example number 2. With example number 2, our function is x of t is equal to 6 times t times the exponential e to the minus 5t plus e to the minus 3t. Okay, so again, we have two terms. We're going to deal with them individually. And the Laplace transform of my function is equal to, let's do this first term. Well, this first term, we have a t times e to the minus 5t. And we have a 6. Now we know from the property of linearity that we can take the 6 out of our Laplace transform and multiply whatever our transform is by the 6. So let's look at what entry will help us here. And it looks like we're looking for a t times an exponential. So here's an exponential, but it doesn't have a t times it. The one below it has a t times an exponential right here. And it's going to matter what our value of n is and what our value of a is. So right now for us, n is going to be 2 because this is t to the 1, and 2 minus 1 would give me a 1. So n is equal to 2, and a right here is going to be equal to this 5. Okay, so now let's deal with this second term right here, which is e to the minus 3t. Now this is just an exponential term. It doesn't have the t on it, so we're going to have something that's going to be a different entry. As we look through our table, we see that entry number 6 is just an exponential term. And entry number 6 is 1 over s plus a. And here our a is going to be this 3. So we have a is equal to 3. Our Laplace transform is plus 1 over s plus 3. So again, this one was pretty easy. Pretty straightforward, but this is the Laplace transform that we have. So now let's do example 3. And what I've done is I've changed the x of t to a g of t to avoid some confusion when we're working with tables. But this function is equal to t times times e to the minus 3t times the sine of 5t. So there's 3 terms in here that have t in them that would have their own, you would think to find in the Laplace transform table. But all 3 of these terms I don't have an entry for all 3 of these terms. So I'm going to go through my properties to see if I can divide this up in some way, this function up in some way. And it looks like I can. When I get down here to entry 7 and 8, I have something that looks close to what I have in this example. So number 7 says it's e to the minus at times some function x of t, and that's why I changed it to a g of t, because this x of t is not this main function that we're working with. It's a broken up part of it. And then number 8 says it's t times x of t. So we're going to do it both ways. We're going to start with entry 7. Now, what entry 7 says is e to the minus at times x of t. So we're going to define x of t as what's ever not this e to the minus 3t. So this is going to be t times the sine of 5t. And this is the entry we're going to look for in the table. But first, what is this actually telling us? Okay, it's saying right here, we're going to take the Laplace transform of my function s, but instead of using s right here, s is going to be equal to s plus a. Fine. So when we look at through our table, we see entry number 28 is what we're going to be using. Here, b is going to be equal to this 5 from the sine. We also need to keep track of an a from this s plus a, and this a is equal to the 3 from this e to the minus 3t. Okay, so the Laplace transform of this function, g of t, is going to be equal to, we just need to read this entry out. So 2 times b is 5 times s is s plus a, which is s plus 3, divided by s, so s plus 3 squared, right? We're substituting the s plus a, plus b squared, which is 25, and this entire term is squared. Now, let's just clean this up. So if we clean this up, we'll have 10s plus 10 times 3 is 30, divided by s squared plus 6s plus 9 plus 25. This 9 plus 25 can combine to a 34. And this denominator is squared. And this is the Laplace transform of our function. With this table entry, and this one was sort of straightforward compared to entry 8, which we're going to do right now. So entry 8 is a little bit, I feel, more involved. In entry 8, if we look at what's happening, okay, so we have t times some function x of t. Let's define x of t this time. Instead of being t times the sine of 5t, we're going to make this e to the minus 3t times the sine of 5t. And if we do this, we can still use entry number 10, right? E to the minus at times the sine of bt. A and b stay the same. The 3 and the 5 stay the same. And what we have to do is, let me get a darker color, but what we have to do is we have to take the derivative of our Laplace transform with respect to s. So first we need to take the Laplace transform, then we have to take the derivative, and then there is also a minus sign that's hanging out over here that we don't want to forget. So first step, let's figure out what our Laplace transform is. So our Laplace transform, x of s, is going to be equal to b, which is 5, over s plus a squared, s plus 3 squared, plus b squared, which is 25. This look familiar? It's this right here. So when we clean this up, we'll get, this is going to be s squared plus 6s plus 34. Now, so we have the Laplace transform of x. Now we need to take the derivative of the Laplace transform with respect to x. And we have a minus sign. So let's first just take the derivative. So d of my Laplace transform with respect to s. And I'm going to write this so everything's in one line. I work with derivatives better when I'm working with everything in one line rather than denominators. So this is to the minus 1. Okay. Now this shows me this is going to be the chain rule. If this is equal to u, right, we're going to do the outside. So this is going to be equal to minus 5 times u, or s squared, plus 6s plus 34 to the minus 2 times the derivative of u, which would be this inner term. So times 2s plus 6. Okay, now let's just clean this up. So this is going to be minus 5 times 2s plus 6 over s squared plus 6s plus 34. This is squared, and this is very familiar, right? This is equal to minus 5 minus 10s. Actually, now we should deal with this minus sign. So this minus sign right here in the this term is going to cancel out with this minus sign right here, right? This minus the derivative, so it cancels out. And then we'll have this 10s plus 30 divided by s squared plus 6s plus 34, and this term is squared. Now, if you look at it, this is the same answer that we had already obtained using entry number 7. So if you had seen entry number 7, great. I think it's a little bit more straightforward, but maybe your table you're using doesn't have it and you have to use entry number 8. You still can, you still get the same answer, a little bit more calculus involved, but you, again, still get the same answer. So hopefully these examples have shown you how you can use your tables to take the Laplace transforms of various functions.